for this problem, we have a lot of circles. Now, this is from the 2016 Aime I number 15. Circles omega 1, omega 2 intersect at points x and y. Line L is tangent to omega 1, omega 2 and A and B respectively, with line AB closer to point x than to y. Circle omega passes through A and B, intersecting omega 1 again at D not equal to A, and intersect C not equal to B. The 3 points CYD are collinear, XC is equal to 67, XY is equal to 47, and XD is 37. Find AB squared. Well, okay, these three numbers are not nice, right? They're odd even prime, and we need a square. So this problem is actually not that computation friendly, which means it's actually really hard to brute force this problem. So first we're going to start with the diagram. We have the two circles. This is omega 1, this is omega 2. Now I'm going to actually make this larger. Then we actually have an L line. Line L tangent to both circles. So it's impossible for them to be both internally tangent. So we have this line. Calling this point A, this point B. Now, from this diagram, we have AB is actually closer to x than y. So we're going to label this point as x, and this point as y. And now we have now AB now wait, let me see the problem statement, sorry. Now circle omega passes through A and B, intersect omega 1 at D and omega 2 at C. So let's say the such circle is like this. It's kind of hard to draw the diagram, but since we need the points to be collinear, then we can actually first draw x and first draw C and D. This will actually be a better idea. So this will be collinear. Then we're going to actually draw the circumcircle. The circumcircle is just the small circle that actually contains all of the 4 points on the on the circumference. So now we're going to actually draw the third circle. Yeah, we're done with our circles. So now what's happening here? Now the 3 points are collinear. Bro, okay. My drawing didn't even make it to be collinear. Now it is collinear. So we're gonna draw the circle again. Like in a test, you always have to like try to make sure you draw like a good diagram. And these 3 points are collinear. Then we're going to draw some line segments. We have this line, and we also have this line. Now I have the 3 lines. XC is equal to 67, XY is 47, and XD is 37. So I'm going to actually expand this. Then we have this point as so we actually got our line segments. Now what are we going to do? So we need to find AB squared, right? AB is actually nowhere from this problem statement, which makes this actually really challenging. We have like the 3 random line line segments that did not even intersect AB, and this is like a random floating quadrilateral in the middle. So how are we going to actually solve this problem? How is that even possible? Now, I have to introduce something called power of a point. Let's say we have a circle. That's a bad circle. Let's say we have a circle, and we have a point outside. Then we actually define the point, the power of this point, as we connect, let this be the center, O. Then we're actually going to draw a line that is tangent to the circle that passes through this point, A. So we're going to draw this line 10, the tangent line. Now tangent line means that if we draw this line, then this is actually a right angle. So now the power point is defined as OA squared minus R squared, which R is just the radius of this circle. Now, by the power point, then we have two secant that is intersecting. Then let's say we call it A, B, C, D. Then because this point with respect to the circle have an equal power, right? Then we have A times A plus B is equal to C times C plus D. This is actually the famous secant theorem. Let's just erase this part and move this back. Now, something actually motivates us to like extend these two lines. Then also extend this line. Now, pause this video and try to see how can you possibly prove that all three of these lines, line AC, line BD, and line XY, all intersect at the same point. Why is that? Well, we can see that, let's call this point P. Then now we can prove that Px times Py is equal to Pb times Pd, and is equal to Pa times Pc. Well, this is actually true because of power point, right? Py is actually secant to the circle of omega 1, and Pa and Pc is also another secant of circle omega 1, and Pd is a secant of omega 2, and XY is actually a secant of both, right? Of both of Px and Pu, both of omega 1 and omega 2. So we get the idea that Pa times Pc is equal to Pb times Pd. Oh yeah, this is actually a really important observation that will actually simplify a lot in the later calculations. Now let's probably keep that aside. Now we're also going to use the PowerPoint terminology again. You see that how a point is actually really powerful with respect to a circle. Now we have two circles intersecting, and we connect the two intersections, and we draw a common tangent. Now, let me zoom this in. Then we connect this and call this point X. Call this point A, call this point B. Oh, don't this configuration looks actually really familiar? Yes, that is correct. This is actually almost exact the same of this part. So now, is there anything special with X? The hint would be actually try to use power of point. Yeah. Now let's call this let's call this point small a, call this point small b. Now, well, actually this is kind of weird, but let's call this p, call this q. Now, line xq is actually a secant of both of the circles, right? Because it's an intersection. Now, actually, the tangent is just a specific, like a special case of secant. It's just when the part inside the circle is equal to 0, right? So this, if we start from point P, then just this part square by the definition of a secant theorem. Since tangent line is just a specific, no, like a special case of secant. Now, since the power point of x with respect to both circles are equal, then we know that x must lie on the midpoint of AB. So AX is equal to BX. Now this is actually pretty powerful. Let me just erase this part. Now let's zoom into this picture again. Now we zoom in this picture again. Now what if we call this point the intersection? Call this point x. From the terminology that we just proved out, AX is actually equal to BX by power of a point. So x lies on the midpoint of AB, and AB are both tangent to, and A is tangent to omega 1, B is tangent to omega 2. So now what's next? We still don't have any silence, except for 67, 47, and 37, right? Now we're just going to let, just zoom in again, let this part be equal to y. So if we let this part be equal to y, then this part is also equal to y, right? Now we use the actual power point, and we can actually try to make some silence. I'm not going to use y since it's going to be confused with the bottom y point. So I'm actually going to use b. So this part is also b. Now, what is the relationship? So b squared is actually equal to, let's not call the middle point x. It's really like a weird. Let's call the middle point c. Then b squared is actually equal to c plus 47 times c. Right? This is actually by power of point. Now we need to find 4b squared. Since the problem statement asks to find ab squared, and b is equal to, and b squared, and b is equal to ab over 2. Now we need to find 4b squared. And how are we going to do that? Now we actually need to find c. So c, we either need to find numerical value of c, or we can actually get an expression of c if possible, a relationship with xc and xd. Now from that, I'm actually going to do a little bit of angle tracing. So we're actually going to complete these two cyclic quadrilaterals. Just use blue. Now, is there anything like that we can actually find? We finally can use the statement that CYD are the three collinear points. Collinear means that it actually lies on the same line. So if they're collinear, then we can say that this angle, let me just make this to be greater in size, this angle and this angle are actually supplementary. So their sum is actually equal to 180 degrees. And now we look at this cyclic quadrilateral. Well, it's actually obvious that this line is a line, right? So therefore these two angles, this angle and this angle, are also supplementary. So it's actually enough to say that we can actually do continue some angle tracing. Let this be alpha. Wait. Let this be alpha, then this is actually alpha. Since in a cyclic quadrilateral, if this is alpha, then this is 180 minus alpha. So like the diagonal angles are the same. And this is alpha. Right. Then this is actually 180 minus alpha. So in fact, this quadrilateral right over here is another cyclic quadrilateral. Wow, we actually found out a lot. So now we actually have the two diagonals of a cyclic quadrilateral, and we can continue some angle tracing right there. And furthermore, we also have to remember the tangent statement, right? Let this angle be alpha. Okay, so if we let this angle be alpha, then not alpha, but be beta. Then expand this, we also have this angle is equal to beta. If we have this angle equal to beta, then they have this angle is equal to beta also. Oh, shoot. This angle is equal to beta. Now do the same thing with this angle. I just call this var phi. Then this is var phi, which means this is var phi. Now what? Now we actually found a pair of similar triangles, which is this triangle and this triangle. Right? These two triangles are actually similar in pair. So now what can we do? We can actually use these two lengths. We're actually making use these two lengths, 67 and 37, right? Now, you see that the twos for both of the triangle, this side actually corresponds, right? And so basically, when we multiply by xc and xd, then we get this entire thing square. Yeah. So now we actually get that, if we call it the top point P, they actually get that px squared is equal to 7 times 37. Now we actually need to find px, since we set its C to be Cx, right? We let C to be Cx. So we can find Px, then we can actually find Cx. So how are we going to find Px? Well, for Px, we actually want to utilize so for PC, we actually want to like use Px. So Px the square root this multiple of this product. And PC okay. Now, well, something we know that this is actually also a cyclic quadrilateral, right? By the angle tracing we just did. This is also a cyclic quadrilateral. Now, can I possibly do another thing that's special to get some more hint? And find px minus pc. Well, something to notice is that C is this is like the beginning thing, but C is the midpoint of AB, so like PC times CX is equal to, oh wait, yeah, let me just use this. Yeah, so now we're going to still use PowerPoint. PowerPoint is actually so powerful in this problem. So PC times CX is equal to is equal to AC squared. No, we can't even call the midpoint C. It's call it Z. Alright, it's equal to AZ squared, and that is equal to ZX ZY times ZX. So these two cancels. We get PC is equal to ZY. No, PZ is equal to ZY. So this tells what? This actually tells that Z is a midpoint. Z is the midpoint. Now, if Z is a midpoint, then we actually find some relationship. Px is equal to square root of 67 times 37. Now Px minus now Px plus 47 is equal to 2C. No, Px yeah, P of x Px minus C times 2. Yeah, Px minus C, or C is just the length of Zx. Px minus C times 2, and then minus 47. That is equal to C. No, that's equal to Px. Yeah, so 2Px minus 47. So C is equal to Px minus 47 root 2. And by doing some of these, and then by substituting into this, then we get C times C plus 47 is equal to root, yeah, wait, what, minus 47 over 2 times root 7 times 37 plus 47 over 2, and then times 4. So it's just 67 times 37 minus 47. Now, even though this algebra is kind of annoying, but we still have to do it. But we can actually simplify a little bit. 10 minus 47 squared. This actually only remains 2 minus 10 minus 20 times 10, which by computing gives us 270 as our final answer. Thank you for watching, hope you enjoy, and I will see you in the next video.